Okay, let me begin by thanking all the organizers for this invitation and providing this platform to speak. So I'm going to talk about bivariant homology theories for non-commutative spaces, so it seems appropriate to begin by telling you what I have in mind when I say non-commutative spaces. So to this end, let me first actually introduce some notation. I mean, this will just stand for the category of all C-star algebras. And it contains an interesting subcategory of all separable C-star algebras. Maybe I'm writing too big. I will have to erase. If I reduce the font, perhaps you can still read. There's something that we learned at the beginning of the summer school, I mean, in Ralph Meyer's lectures. In case you were not present and you are not aware of it, let me just remind you that there is this Gelfand-Naimark theorem. At least one way to formulate it would be as follows. If you look at the opposite of the category of commutative C-star algebras, then that would be equivalent to pointed compact spaces. Yeah. And since this event is organized by the Hausdorff Institute, so I think that treating non-Hausdorff spaces is a blasphemy. So I won't explicitly write it down. Now there is an old question, and so the question is rather in rather vague terms. What about, can we do homotopy theory on this category? So this question can at least be traced back to the works of Efros and Rosenberg. I mean, Rosenberg explicitly asked the question, for instance, if you have pointed spaces, then you can always do two natural things. You can smash it with the pointed circle, and you can also take maps out of pointed circle, pointed maps into. And one of them has a counterpart, the suspension functor in C-star algebras. What about the other one? And this is already leading to something like this, that question, and it was answered positively by Chris Phillips using pro-C-star algebras. But I want to quote another theorem now, which makes the question precise, and this is due to Quillen. So Quillen basically introduced this machinery of model categories, and he convinced us that homotopy theory on any category C is the same as a model structure on C. So in this sense, you can make this rather vague old question precise. And let me at least try to give you some idea. Well, no. So what I want to say is that he introduced this notion of model categories, and the theorem part is that he showed that all the expected constructions from homotopy theory can be performed in the presence of a model structure on any category. So now the definition part. So a model structure on a bicomplete category C is a choice of three subcategories. And these three will be denoted by the weak equivalences, the fibrations, and the cofibrations. and let me just say plus many axioms. I mean, I won't reproduce them. It makes no sense. But the point is that the important thing is that when you have a choice of 3 subcategories on some bicomplete, by that I mean it has all limits and co-limits, then this is somehow the most important thing. In homotopy theory, as you know, you want to study things up to homotopy equivalences, and homotopy equivalences play the role of weak equivalences. So those are the morphisms in your category that you would want to treat as isomorphisms in the homotopy category. And so whenever you have a model structure, then it has a homotopy category. And the homotopy category is denoted like this. And this is just the fraction category like so. So where W is just the arrows in your chosen weak equivalences. So this basically determines which arrows in your category you would like to invert to arrive at the homotopy category. And one consequence of this model structure, if you like, that's a theorem part of it, and I will now really squeeze it in here, is that the homotopy category is equivalent to some subcategory of so-called cofibrant-fibrant objects on C modulo homotopy. So you see here this category of fractions, what it does is that you can prove its existence up to some problem like set theoretic problems by pure abstract nonsense, but then understanding the morphism sets in the homotopy category is quite difficult. And if you have this kind of equivalence, and in order to arrive at these cofibrant-fibrant objects, you need these 2 subcategories. They sort of help you decide which objects should be considered cofibrant and fibrant. Then the morphisms in the homotopy category can be expressed quite neatly by just ordinary homotopy classes of maps. And so it also shows that you don't arrive at any set theoretic problems which you would otherwise encounter if you just naively inverted all these arrows. So I think it is, if you are seeing this for the first time, it might be very abstract. And so what is helpful at this point is to look at some examples. So example 1, if you take C to be compactly generated weakly Hausdorff spaces, I mean, since we are not physically present at the Hausdorff Institute, weakly Hausdorff is still okay, I think. So this category has a canonical choice. So I want to, this is the set of maps which are just which induce isomorphisms on homotopy groups. And the homotopy category of this is precisely called the homotopy category of spaces. So but the good thing is that the homotopy category here can be described as this admits if, for instance, X and Y are CW complexes. Right? So up to homotopy, you can find by CW approximation some CW spaces, and then the morphisms are just given by homotopy classes of maps between them, things like this. Yeah, so these are cofibrant objects. And everything is fibrant. And example 2, I mean, so if you put C to be the category of unbounded chain complexes on some ring R, and you choose W for which is the arrow category of the weak equivalences, these are just quasi-isomorphisms. So these are maps between chain complexes which are just isomorphisms at the level of homology. Then the homotopy category has a name called the derived category. So this is precisely the homotopy category. And once again, I mean, I'm talking about this example because I might need this object later on. But the point is that once again, like here, at least if your chain complex is nice, for instance, it's a bounded complex of finitely generated projective modules, then again, a simple description like this, chain homotopy classes of maps, would describe the morphisms between those things at the level of the derived category. So based on all these things, the real question, the new question that you should ask is, does there exist a model structure on C star? Yeah. If you ask in this generality, then the answer, I mean, a trivial answer is yes. But the problem is that it's not doing anything interesting. The model structure on C equal to C star. So the model structure on C will be just, oops. So if you choose your weak equivalences to be isomorphisms, it can be completed to a model structure. It is not, the homotopy category is not changing anything. This is not what you want to ask. So the real question that you should ask is this: does there exist a model structure on this such that the homotopy category actually models what is called the homotopy category of C star algebras? So this we know. This is a well-known object in the world of C star algebras. You have a notion of homotopy between star homomorphisms. You go modulo that equivalence relation. Then you arrive at the homotopy category of C star algebras. And the question is, can you find something which satisfies this condition? And the answer then so the answer now is actually a theorem. This is due to Anderson and Grodal in some unpublished work, and then Joachim and Johnson, they became aware of this when they constructed their KK model structure, and then a final published account also appeared in the work of Uwe, Otogo. So the answer turns out to be no. And this means that the question is nice, but you really have to do something about it. I mean, in this way, you cannot solve the problem. And the next best thing that you can do is mu squared question. So does there exist a model structure on C that, let's say, contains C star, or for technical reasons, I would now look at separable C star, such that the homotopy category of C, again, contains this? This is the question that I would like to address. And then it's a theorem due to Hausdorff, and then using different methods, we arrived at the same, so the answer is yes. So Hausdorff basically used purely model categorical techniques, but I found it much easier to use infinity categories, and using those things you arrive at the following picture. So there is a category called NS star, which I call the infinity category of non-commutative pointed spaces. It contains an infinity category, the opposite of an infinity category whose objects are separable C-star algebras, and this would be your infinity category of non-commutative pointed compact spaces. So these are not necessarily compact, these are like analogs of this compactly generated spaces, and this thing basically supports a model structure. So on the category of so this infinity category is nice enough that you can extract a model structure out of it and indirectly give a positive answer to this question. So it also has the following property, that any infinity category has a homotopy category. So the homotopy category of an infinity category is always denoted by writing a little h in front of that, and this will be So this will contain the homotopy category of this, and this is equivalent to Ho C star, and this is what you would call the homotopy category of non-commutative pointed spaces. So it's time to erase the boards, and in the meantime, let me just try to tell you, I arrived at this question a long time ago via completely different considerations right after my PhD, but I was not really, at that time, was not well prepared to address this question. And it was like trying to climb Mount Everest without any preparations. And so I made some ad hoc attempts, didn't quite work out. What I was missing really in my toolkit is this language of infinity categories. So this is something very useful that has emerged. It escaped my attention for some time, but now, fortunately, I have assembled all the resources to begin my ascent. And in the next course of whatever, I do not know how much time is left, I'm going to tell you some of the interesting things that I have encountered during this brief ascent period. And infinity categories, you have already learned from the lectures of Ralph Meyer what two categories are, and the word simplicial set was also used. So infinity categories are really simplicial sets, or at least one model of infinity category is the quasi-category model due to Joyal, and that's a simplicial set satisfying some conditions, and it has been enriched and studied very extensively by Lurie, and so now it's a very complete package that you can use. You can, or at least I think I can get a lot of mileage out of that. So, having situated ourselves at a stage where we can now try, we think we understand what non-commutative spaces are or pointed spaces are. They are really built out of C-star algebras by some formal procedure called colimits, filtered colimits. And these things take place in an infinity category, so the appropriate notion is actually infinity filtered colimit. And using these things, now we can talk about bivariant homology theories. So So actually, the title is a lie because I won't really talk about bivariant homology theories. I will talk about a special class of them, but it helps if you look at some examples first. So the first example is actually KK theory. However, it is not really KK theory, it's E theory that I have in mind, but I am deliberately going to confuse between the two. And a theorem, like often quoted and cited theorem of Meyer and Nest, is that this category KK is a triangulated category. So fortunately, my talk comes after the talk of Ralph Meyer, where he already explained these things. So I am not going to waste time in recalling. I mean, you cannot improve upon perfection. So that was done perfectly there. And now we know what this is. And just let me recall that that if you have an extension of this type, and this is the word which separates this is the word that separates the two theories. So if you have such an extension, then it induces an exact triangle in KK. Of course, I forgot to write down the diagram. So there is something like this. What is it? Well, yeah, SC star goes to KK, and it's homotopy invariant. So it actually factors through the homotopy category of separable C star algebras. So there is some canonical functor like this. It is homotopy invariant, so it factors through the homotopy category, and it has the property that if you have an extension diagram here, then this functor will map it to an exact triangle in KK. So the definition, I think I saw it first in the thesis of Thom, and this is called a triangulated homology theory. So a triangulated homology theory is basically a functor which looks much the same. So the target is a triangulated category. And again, it factors through the homotopy category. So it's homotopy invariant, and it has exactly the same property that if you have some kind of extension, semi-split or not, then it gives rise to an exact triangle in the target triangulated category. And a second example that we might want to look at is this. This is again, so a diagram like this. You have, I put directly this functor from the homotopy category. This goes to something called non-commutative stable homotopy. That's the name in the literature, but there's very good reason to call it non-commutative finite stable homotopy. Anyway, I don't want to mess around with the terminology. And this sort of can be completed to a diagram like this. And this is a localization of triangulated categories. So this is an L. And this package is very beautifully explained in the book of Kunz, Meyer, and Rosenberg. So much of my knowledge stems from that. And this non-commutative stable homotopy, at least one way to If you have two C-star algebras and you want to understand what are the maps, then this is just given by this famous Cohn-Higson construction. This is asymptotic homotopy classes of maps. This is the group. So the question at this point is, I told you that, did I tell you? Yeah, that this is only compact spaces. This is all non-commutative spaces. I have a theory that seems to be defined on pointed compact spaces. Can I extend it to this whole thing, enlarged thing that we have? And of course, we want some, in order to avoid some trivial answers like the one here, you would want to also impose some more conditions. It should not be a trivial enlargement. It should satisfy some properties, which I am going to explain. So the question is, so how to go beyond this category of separable C-star algebras? And, well, let me just remind you that what we have is this. And we would like to go to something which contains the homotopy category of non-commutative pointed spaces that I just erased. This hopefully will go into some triangulated category which replaces that as the target, and this goes into another triangulated category, and there is a functor R. And remember the contravariant equivalence between the Gelfand-Naimark. So this was already receiving a map from the opposite of the category of separable C-star algebras. So in order to faithfully extend this diagram, I have to put op everywhere. So this is what we want, and we want some compatibility conditions. So moreover, we want, number one, this functor for good reasons will be denoted by sigma infinity. It is like a suspension spectrum, those who are familiar with this construction. If not, it's just a name for you. So sigma infinity should preserve coproducts. Preserve coproducts. Plus it should have some more compatibility. This will be actually a symmetric monoidal category, so it should be a symmetric monoidal functor. It won't play a major role, so I don't want to write that down. And number two, this R should be Bouwsfield localization. By the way, these are both they are both assumed to be triangulated categories, much like the target of triangulated homology theories. And so these should be Bouwsfield localization of triangulated categories. In other words, the functor into its essential image so it should admit a fully faithful right adjoint. That's the point. yeah, that's the way to think about it. And the theorem in this setup is this this above or left-hand side picture exists. And for me, this tau 1 is what I call the homotopy category of, so this has a name called the homotopy category of non-commutative spectra. And this tau 2, this is what I would call an infinity categorical version of KK theory, but it's opposite because of this op floating around everywhere. And this is really obtained as a Bausfield co-localization. Did I write? No, this should not be localization, this should be co-localization. Yeah, so co-localization means instead of having a fully faithful right adjoint, it should have a fully faithful left adjoint. So that's the point. So in some way, this tau 2 is an answer to a model structure, because these things are nice triangulated categories. They are compactly generated triangulated categories. So they are both compactly generated. So those who care about things like Brown representability and results of that nature, they know how important this condition is. So standard constructions, NSH and KK, I'm not sure if they're compactly generated, probably not, but this one is. And it satisfies Brown representability in complete generality. And this picture arises as a, so the remark here is that this diagram is really a homotopical shadow so there is actually something more fundamental that's happening. So you, instead of going to the homotopy categories, you directly stay at the level of infinity categories, and then you have a diagram like this, and this goes to something that I would call KK infinity op. And there is a commutative diagram. If you apply homotopy categories to this thing, then you arrive at that. And these are all, I mean, this is the fundamental diagram. You have pointed spaces. By suspension spectrum functor, you go into non-commutative spectra as a localization, which means, and because it is a Bausfield localization, this really can be seen as a subcategory after applying the left co-localization. So after applying the fully faithful left adjoint. So this really can be seen as something sitting inside that. And now out of this general machinery, you can get something concrete, something that you can probably digest. And this is what I intend to do. According to my notes also, it's time for a comic relief. But I didn't have the time to prepare any joke appropriate one. So while I erase this, if somebody finds something appropriate to say, can... Yeah, sure. I could try to turn it into a joke. Okay.
The question is the category of commutative spectra, so CW spectra, for example, somehow fit in T1. What's the reason for the
T1, where is T1?
T1,
Oh, right, yeah. Yes, it does. It does. This is once again, I mean, Lurie characterized that as the universal stable infinity category generated by one object, and this is a many object version of that. The zero sphere also sits inside that, but it contains more non-commutative spaces. All right, so if nobody wants to chip in, I will continue with the boring stuff. So I open a third section. This is called the bootstrap category. Masood, when did I start and how many minutes do I have?
You have here 4.
Okay. So the bootstrap category, it starts with this notation. I mean, let me denote by this funny one, this object which is R followed by sigma infinity of C. So let me remind you that this is homotopy theoretic shadow. This is called the colocalization functor R. So this already contains SC star op infinity. So in particular, this contains this object C. You can go inside this, then follow it up like that, and that object I denote by 1. And let me call HKK infinity prime. This is the co-localizing, so I'm getting a bit worried by all these things. Co-localizing subcategory. I left my notes unattended, and so arrows might have reversed, and localization. Co-localization might have, but I am hoping that it is really the co-localizing subcategory of HKK generated by this object 1. So co-localizing subcategory just means that you start with this object, you perform all the basic constructions that you need to perform to arrive at a triangulated category, so translations, both directions, mapping cones. But then you have to close it up under products. And if you consider, localizing subcategories, then you would need to close it up under coproducts. Yeah, so that's the difference. And in this setup, there is a theorem. So many parts. Number 1. Well, let me set tau to be HKK prime this whole thing up. This will simplify life. So this tau admits an algebraic description. This is the derived category of this ring. And I hope you still remember the construction of the unbounded derived category of a ring like this, which I explained. It's unbounded chain complexes modulo quasi-isomorphisms. And the warning here is that this is an algebraic description that might give you the feeling you understand it very well, but the functor that's implementing this equivalence is weird. It's only an additive isomorphism, additive equivalence. It's not clear whether this functor preserves exact triangles. So that's one of these Bausfield-Franke exotic models. So unless it participates well with exact triangles or interacts well with exact triangles, I mean, you still can do something with it, but it would be very nice if one could show that it is an equivalence of triangulated categories. So I just mentioned it. Let me just write. This is Bausfield-Franke and written up very beautifully by Pachkoria, the exotic model. And number 2, I need a lot of space for that, but let's start here. So if I set pi star of x for any object to be this graded Hom, tau sigma star 1x, this object for all x in tau, then you can for all xy in tau, there exists a natural short exact sequence, and the short exact sequence is very predictable. So it will have an x term, pi star of 1, pi star of sigma of x, pi star of y, tau of xy, Hom pi star x. So it is the universal coefficient theorem, if you can recognize the pattern. The Hom is over, so the handwriting at this point is irrelevant, perhaps. So the Hom is over the graded ring pi star of 1, and it is this. But if you look at it carefully, it is really a k homological UCT. It's trying to express the KK theory groups in the opposite category in terms of the k homology groups. So I'm not sure how useful that is going to be, because normally I think people know how to compute k theory. They compute k homology using kk UCT. And so this is asking you to directly compute the kk in terms of k homology. I do not rule out any, I do not want to declare it to be completely useless just because of that. And what I know, it seems to me that if A belongs to us, so if you start with the separable C star algebra that is nuclear with finitely generated K theory plus satisfies UCT, then this R of sigma infinity of A belongs to the bootstrap category. So at least under, the ordinary UCT for C star algebras and this bootstrap category has some intersection, and in that intersection lies these algebras. And now finally, with all these things, I would like to finish it off with something that I was thinking about a long time ago, namely topological T-duality. So this is where I'll do a very haphazard work, because I have very little time left, and also everything is not really fresh in my mind. But I think because I started thinking about these things based on these considerations, I wanted to finish it off with this story. So there is a theorem, it's a relatively recent theorem due to Bloomberg, Gepner, Tabuada, and it says that there exists a stable infinity category of non-commutative motives. So, and the notation is M-lock. So the objects in this are themselves some kind of stable infinity category. So it's like an infinity category of stable infinity, or a stable infinity category of stable infinity categories. We don't have to worry about all those things. What is quite important for me and for anyone who's interested in non-commutative motives is this catchphrase that it is the universal cohomology theory for non-commutative spaces in the sense of Kontsevich. So this construction of non-commutative spaces that I explained is really following the spirit of non-commutative geometry advocated by Kohn, whereas Kontsevich, motivated by algebraic geometry, came up with this idea of, let's say, non-commutative derived geometry. I'm not sure what is the precise terminology there, but he said, let's treat derived categories or differential graded categories as non-commutative spaces and try to build a geometry starting just from that. And these things got more sophisticated with the advent of this technology of stable infinity categories. So now, instead of working with DG categories, it seems to be profitable to embed that inside this stable infinity category of non-commutative motives, and then this becomes a universal cohomology theory for non-commutative spaces. So that's the importance, as far as I'm concerned, of this setup. I hope this is the last time I'm doing this. No, now for them non-commutative space is a stable infinity category. So if non-commutative motives, yes, so it is also the same. But the point is that the morphisms, so if you know how, let's say, standard motives are constructed, you first start with schemes, then by some Yoneda construction you embed them fully faithfully, and then you do some localization and the morphisms change. But the objects can still be via Yoneda functor seen as objects. Every space gives rise to its motive. In the same sense, every stable infinity category with some geometric condition viewed as a non-commutative space gives rise to its non-commutative motive, which is itself a stable infinity category. So, in the last few minutes, so where am I? So, there is a theorem, and the theorem says that for any there exists a non-commutative motive which is denoted by mk of A, and this belongs to M-lock, this non-commutative motive category. And this construction satisfies the following compatibility conditions. So this goes to Mk, this goes to M-lock, and then this goes to Kk. So the motivic categories, the motive functor sort of factors through Kk, and there is something K because there is a functor just called just M, and this needs to be dressed up with a K, and then this happens. It doesn't matter how it's done, but there is a way to stabilize the motive functor in such a way that it factors through this. And what I would like to prove, this is in progress, but it will be written up in some reasonable time, that all of this extends, right? This sits as a subcategory of that, So what am I going to write here? You probably can guess. This motive functor extends to all non-commutative spaces. But because of the contravariant duality, this sits inside the opposite of that. So if I want to extend it, I put an op there. And then this factors through R sigma infinity, kk infinity op. This. Oh, yeah. So the point is that this diagram should be generalized to that, so that you have some kind of non-commutative motive as attached to any non-commutative space in the sense of Alencon, and then you end up with its motive, and then you can compare the topology at least of that space with the topology of the motive, which is a space in the sense of Kontsevich. And now I want to tie it up with T-duality in the last. So T-duality is, for me, it's just topological T-duality, so I will disregard all the geometric aspects and so topological T-duality it's just an involution, if you like, on the set like this, where X is a space and H is some integral cohomology class, and you want some property that if XH and if these two are T-dual, then there is some twisted K-theory isomorphism. So isomorphism with a shift. Now, Jonathan Rosenberg, he showed that associated to any such pair, at least if X is locally compact, you can associate a C-star algebra such that K-theory, topological K-theory of this C-star algebra is the same as the twisted K-theory of this pair. And finally, there is a theorem by Brodsky, Matai, Rosenberg, and Szabo, which says that if they are T-dual, these two, T-dual, then out of it, using the Kohn-Skandali's picture of KK theory, you can construct an invertible element in KK1 of CT X H CT X prime H prime. And this you should think of as an element, let's say, in this, and you suspend this second variable. Okay, and what does it mean? This means that if these two are T-dual, then these two C-star algebras are KK equivalent. But if these two C-star algebras are KK equivalent by this construction, then non-commutative motives are isomorphic in the motivic non-commutative motive category. And this means, because this is the universal cohomology theory for non-commutative spaces, in some sense this is the sharpest possible result that you can expect from this sort of setup. Where, oh, and I forgot to mention here that this construction has the property that to any non-commutative motive you can associate its K-theory, and the K-theory of the non-commutative motive of A is isomorphic to the topological K-theory of A. So if you have an invertible element in here between these two things, by this kind of diagram, they become isomorphic here. Then you apply K-theory, you get isomorphism at the level of K-theories. And these two, by Rosenberg's theorem, this is the twisted K-theory isomorphism that you would expect if two pairs were T-dual. So I would like to summarize it as by a catchphrase that topological T-duality is really a statement about isomorphisms of non-commutative motives. Okay, thank you very much for your attention.
Questions or comments?
Jokes?
No, no. Okay, so let's thank Snigdhayan.